Hello, this presentation is in regards to traffic and equilibrium routing for CEE 372 Transportation Engineering, Spring 2021. This is presented by Royce Perez, Limi Sunjo, Elissa DeWitt, Julian Johnson, and Paul Granillo. What is GMNS? General Modeling Network Specification. It's a flexible and unified multi-mode traffic network representation format. It's a convenient way to share and merge network data from different channels across the globe. It covers a variety of network types, adopts a unified format for transportation engineering. It's suitable for various network modeling purposes. It works cohesively with pandas, a Python data package development software. What is pandas? Pandas, a program developed by AQR Capital Management in April 2008 and open sourced at the end of 2009. It continuously developed and maintained by PyData development team. It works cohesively with Python program available online through Collaboratory. How to use pandas to process GMNS data. Using Collaboratory, it allows to write and execute Python in your browser. It's easy for sharing. Free access to GPUs, graphics processing unit. It's a computer science-based program used to analyze and visualize data, generate data, and use matplotlib to visualize. This is an example of Collaboratory. It's similar to MATLAB. General coding and running process is very user-friendly. GitHub and a demonstration. GitHub is a code hosting platform for version control and collaboration. It lets you and others work together on projects from anywhere. Let's review a live demonstration and concepts with GitHub. So here is GitHub. As you can see, you can add text, you can include code. In this case, we're going to just do a quick demonstration of code that's relevant to this presentation. We'll actually go ahead and collect this code right here. We're going to copy it, open Collaboratory, which I already have a presentation already open. And as you can see, you can add code simply by using this plus code right here, and we'll paste the code. We can execute it with this play button. And right below, it will paste any relevant data that you're sharing with other engineers. In this case, we can format various different types of information in regards to transportation engineering, from node names to X and Y coordinates, node types, control types, and zone IDs. We can also include pivot data information that's relevant to Excel. And we'll continue on with this with Julian. We'll explain a little bit more in regards to those tables.
All right, thank you, Royce. So kind of piggybacking on what Royce had discussed, we did use Python code in order to put that into Collaboratory to generate this pivot table right here. And basically what's happening in this pivot table is we have a number of station IDs with the timestamps to the left of them as well. And it basically shows the density, in which density is determined by the amount of vehicles per foot on any given road or highway. And basically what this density is showing is how congested a roadway is at a given time. So as you see, we have at midnight on station ID, on the first station ID, it's at 0.103, which is a very low density compared to other ones as well. And if we go on to the next table, so our average density is going to be the summation of the densities, the individual densities across a timestamp. So basically at midnight, you add up all the densities and divide by that number of densities, and you get the average density, which is displayed on this table. And so as you see at 11:35 p.m., we're going to have a pretty congested roadway right there. And you might want to navigate to use another roadway at that time because it is going to be a bit slow for as terms of speed of a vehicle. And that's because of the density on the road. And at midnight, we're actually going to have a low density. So you might want to go and use that road so that, you can go faster on that road. And if we go to the next slide, it kind of relates that table to Google Maps. And Google Maps will use this information as well, where you'll have green, which will indicate that we're going to have a pretty free flow. It's going to be a fast-paced road right there, and we're going to be able to go without any congestion really at all. And then as you go to yellow, it's going to be moderately congested, meaning that you might have you will have more vehicles on that road. And as you go on to red, it's going to be heavily congested. And the way that Google Maps will account for that is it might just send you to another route to get to your destination, which piggybacks on traffic routing as well. And so I can go ahead and pass it off to Alyssa, and she kind of gives the breakdown of traffic equilibrium as well.
Thanks. So using the data that Julian and Royce have both explained, you can create a traffic equilibrium equation or method, I guess, to find what that might be for a particular route. For example, this figure on the left is just a Google Maps example of getting from point A to point B. And there are two obvious options. The freeway route, which is highlighted in blue, and the arterial route, which it just means the regular road with stop signs. It's a little slower. There are more cars. And that would be this straight shot road from point A to point B. And the goal is to make every car that's driving on either route get to the destination at the same time. And that's what equilibrium is. And I'll explain that on this Excel sheet. So from the data, these are the numbers that we've obtained, and highlighted in blue in that left corner is the capacity of each of the pathways. So the demand is those two numbers of 4,000 plus 3,000 is 7,000, and that's highlighted in orange as well. So on the graph on the right, we have the x-axis, which is the 7,000 cars that need to get from point A to point B. And no matter what, that number will be used. So for example, if 2,000 cars are using the freeway, it can get to the destination in 20 minutes. But if 2,000 are on the freeway, the remaining 5,000 have to use the arterial route, which will get them to the destination in 60 to 70 minutes, which is not ideal. The equilibrium option has a little line shown up to it. It's where the two paths cross. In the table, it's highlighted in yellow. This number is 5,400. We'll be using the freeway, while the remaining cars would be using the arterial route. And the travel time for everybody involved, for all people driving, would be 30 minutes. And that's what the goal is in routing and traffic equilibrium, is to get everyone from point A to point B in the same amount of time. So that has the least congestion and gives you the optimal capacity for each pathway. Something we have to look out for is called Brace paradox, and Paul is going to explain that.
Thank you, Alyssa. So what is Brace paradox? Basically, it's the observation that adding one more road to a road network can ultimately slow down the overall traffic flow through it. Now, this may seem counterintuitive, so let's dig a little deeper and see what causes this phenomenon. So suppose that we have a road from start to end and can be modeled as t over 100 for the first link, and t is equal to 45 for the second link. When all 4,000 cars are evenly dispersed from start, we're left with a 20-minute drive time on that first link from start to A, and 45 minutes from A to N, which gives us 65 minutes. However, imagine they were to build a small link between A and B, and this small link ultimately takes, for simplicity, no travel time. Initially, the drivers will see some time savings in travel. Obviously they want to take the path of least resistance, so They could ultimately travel from start to end in 40 minutes. But as more people become aware of this route, it starts to become overpopulated and ultimately causes the route to be oversaturated, which causes the latter situation, which T is equal to 40 minutes. So regardless, it increases the overall drive time, ultimately just sabotaging the commute for really the driver's own self-interest. So the moral of the story is that Bray's paradox is something that needs to be evaluated and taken into consideration. And really, any additional capacity needs to be evaluated very carefully. So I'm going to go ahead and pass this off to Lemmy as he explains the impacts that we've seen from COVID and traffic equilibrium. Thank you.
All right, thanks, Paul. So when we're looking at traffic equilibrium and routing, what makes it important? Why is it relevant to us today? So if you look at it in the context of COVID-19, you think before the vaccine, there's less people on the road, there's less traffic congestion. Those who are on the road are traveling from point A to point B. They're doing so quickly and with less traffic. But then as more people get vaccinated and start to return to the road, you end up with more travelers and more people using public transportation, which results in lower quality public transportation and increased roadway congestion on the highway. You'll see lots of traffic as more people or more drivers are on the road. So what is the long-term effects on transport design and what changes might be made to the system or city planning? Well, we can look at that in terms of scenario planning on the next slide. So there are two possible future outcomes, let's say 5-10 years down the road. Scenario one, people are encouraged to stay at home due to virtual work options that were already put in place during the pandemic. So in this scenario, we would end up with less congestion on the road, less travelers, because there's fewer people actually commuting, they have virtual work options, they're actually driving less. And this might actually increase the quality of transportation overall. But then in scenario two, we have more people who are quickly returning to the old normal, or they're going more in person and kind of ditch the virtual methods that were in place during the pandemic. And this results in possibly long-term congestion, a lot of city planning that has to be reevaluated, how we design our roads, and how we can manage and redirect this influx of travelers, and how we can manage the traffic congestion. All right, so I think that's the end of our presentation. Thanks for listening. Do we have any questions?